Hello. Today I'm gonna be finishing my derivative lessons. The second derivative, real world derivatives, and the average versus instantaneous. I already did videos of the derivative at a point, first examples of derivatives and what derivatives tell us, just in shorter videos and without audio. But I'm gonna be finishing the last three today. This is kind of like a math marathon like I did last week, but it's probably going to be shorter. Maybe. I'm not sure how much shorter, but this time I'm only doing 3. Last time I did 4. I guess I'll start now. Yes, I believe last time I did the squeeze theorem, IVT, precise definition of limits, and the derivative at the point. And I did these two, and now I'm going to do the second derivative, real world derivatives, average versus continuous. But I'd rather save these in order. Okay, I'll start now. Okay, the second derivative. As we have seen, the derivative represents a rate of change. What about the derivative of the derivative? The rate of change of the rate of change sounds like a difficult and abstract concept. In fact, it comes up quite naturally in many real-world applications. For example, consider the U.S. national debt and the deficit. The national debt is defined to be simply the amount of money that the government owes to its creditors. The deficit is the measure of the rate of change of the national debt. It is generally computed on a yearly basis and is defined to be the difference between government spending in a given year on defense, social security, infrastructure, and so on, and government revenue in the year via taxes and fees. So it's just calculating how much they spend, how much money they make. If this difference is positive in a given year, then the national debt has increased. If it is negative, then the debt has decreased. The difference has only been negative 4 times since 1970 and 4 consecutive years from 1991 to 1998. In his 2015 State of the Union address, President Obama pointed out that his administration had seen smaller and smaller deficits each year since 2009. Let's try to answer this question. If DT represents the national debt as a function of time, what statement about DT does this fact correspond to? Certainly DT is positive, and it has been for a long time. For instance, D114-2015 was roughly 18 trillion. What about D prime T? Since the U.S. government has been spending more than it's been earning since the early 2000s, DT is increasing, so D derivative T is positive. But this is not what Obama was talking about in his speech. In fact, the president's statement is a statement about the rate of change of derivative T, which is given by the derivative of DT. This is called the second derivative of D, and is denoted D prime prime T. That's probably the easier way. Obama's statement was roughly that for the time between 1/1/2010 and 12/31/2014, the rate of change of D prime T was negative. That is, D prime prime T is less than 0. Do not confuse this with the statement that D prime T is less than 0. Again, D prime T is more than 0. That is, the national debt was increasing. It was just increasing at a slower and slower rate. So the graph of the national debt may look something like this. So as we can see, the debt 2008, 2009, 2011, so on. Yeah, we can see how it was a high increase and then saw how it slowed down, as you can see by this picture. I'll make sure I take a picture of it. The rate of change d prime is negative. That is d is increasing, or debt is increasing, but it's increasing more and more slowly. Notice that the graph is not exactly of the function we have defined at that time, but in fact this graph is of the debt as a percentage of USD GDP, which many economists view as a better measure than debt in dollars. Since GDP rises every year, debt time doesn't increase as fast when measured this way, but the shape of the curve is similar using either measure. The following problems explore the meaning and the usefulness of the second derivative in more detail. Let's look at these ideas in the context of a simple function of x equals x to the power of 2. The function is decreasing on x is less than 0, and increasing when x is more than 0. So the first derivative is negative for x is less than 0, and the positive for x is more than 0. Given that f prime prime describes the rate of change of f prime, telling us where the slope of the tangent line is increasing or decreasing, for what values of f prime prime, positive or negative. So I believe would be relative. It would be probably the same. F prime prime is negative when x is less, positive when x is more. When? Oh, f prime prime is always positive? Here, I guess maybe because it's the increased change, either backwards or forwards. Here, I'll see. Just look at the slopes of the tangent lines and see that they're increasing as you move from left to right, which means f prime is always increasing, which means f prime prime is always positive. The slopes go from large negative numbers to negative numbers close to 0, to 0 at x equals 0, to small positive numbers, to large positive numbers. So the slopes are always increasing. Yeah, that probably makes sense. As that would just be the same with the chart, but I guess it's always constantly increasing. So we can see by this. Given a point of x, function of x on the graph of f prime x tells us the slope of the tangent line there. The second derivative of f prime prime x, also written as derivative to the second power f, divided by the derivative of x to the second power, tells us the rate of change of the tangent line slope as we move away from x. I'll make sure to keep this formula. I wonder if I could copy this. Yeah, a second. I think I could. Here, give me 1 second. Let me see if this will work. It's a little messed up though. Here, let me write the formula. Maybe a second though. I think this is a little messed up. Wonder if I could use this chart to do like over. So, derivative to the second x f derivative x to second times. Let me make sure uppercase as I remember. times. Oh, we have the derivative of x to the second, or derivative to the second times f, and divide. By each other. Tells us the rate of change of the tangent line slope as we move away from x. So the function of prime x is more than 0 means the tangent line has increasing slope, while f prime x is less than x means the slopes are decreasing. So it has relatively the same as f prime, your function x prime. For example, if function of x equals x to the second power, we find that function prime x equals 2x and function prime equals 2. I'll take a picture of that, seems important. So, here, let me copy this. Give me 1 second. This really messes it up. Function of x. Yeah. I wonder how this works. I don't know if there's any way we can insert math equations, like powers and stuff, in this. I don't think so. Okay, we can continue. Sorry, I had to pause my recording for a second. So, I couldn't copy that, but I think I already took a picture. But I might as well take another. So, as we move from left of the origin to the right, the tangent line slopes go from negatively to increasingly positive values, which makes sense since f prime x is more than 0. There you go here. Consider these 4 graphs. Number 1, number 2, number 3, number 4. Well, this looks like rotations. Which 2 are the graphs of functions f, x such that f prime and f prime have opposite signs? Have opposite signs. One and 3. I'm gonna think about 1 and 3, 1 and 4. Actually, probably not. And 3. I don't think they even meet. 2 and 3. 2 and 4. So 2 and 4 and 1 and 3 are just opposite, so I think they're out of the question. So it's either 1 and 4 or 1 or 2 and 3. Actually, yeah, 2 and 3 or 1 and 4. So It seems it's either 1 and 4. A book relative. I don't know which one would be best though. I'm trying to think based on the positive and negative areas of a graph. That would be best. Hmm. I think it may be 1 and 4. 2 and 3. Prime is also decreasing. Similarly, in graph 4, f prime and f prime are both positive. Graph 2, f prime is more than 0, but f prime is less than 0, as in the National Day example in the first pane. Graph 2. Oh yeah, I could see that. Graph 3 is the mirror image. F prime is less than 0, but f prime is more than 0. Oh yeah, you could see. So the answer is 2 and 3. So it was 2 and 3. So I guess I was wrong with. Yeah, so I guess I was wrong with that. I guess instead of getting the 2 ones that were all negative, I got the 2 ones that were all positive. We want opposites, so graph 3 and graph 2. Let me just see why. F prime is more than 0, but f prime is less than 0. National Day example. Yeah, you could see how that would work. As the previous problem shows, the signs of the second derivative is relatively to concitivity. What does concitivity mean? Intuitively, like the graph of a function is not concave up if it looks like a smile, and concave down if it looks like a frown. That's not exactly a rigorous definition, so let's try to flesh that out a little. The graph is concave up at a point if the tangent line at the point lies below the curve. When we zoom in far enough, the graph is concave down at the point when the tangent line at the point lies above the curve, where the zoom is far in enough. So yeah, we could see how basically if like the tangent line lies at the top of the curve, or almost like kind of like the flat point, which usually is considered 0 if it meets 0 with no change. And also the smile and the frown thing will also be just easier too. In the first graph, the rate of change of the derivative f is always positive. The function decreases more and more slowly, and then increases more and more quickly. So the second derivative is positive. In the second graph, the rate of change of the derivative is always negative. The function increases more and more slowly, and then decreases more and more quickly. So the second derivative is negative. Yeah, so we could see like how it decreases. Like in this one, we can also see the concave up, how it decreases more, and then shoots back up. And then the concave down is literally the opposite, where it goes increase, like the function increases more and more slowly, Like you can see as it goes up, it gets slower and slower, and it drops a lot. And then the concave up is just opposite. To summarize, the graph y equals function x is concave up at a if and only if f prime prime a is more than 0, and it's concave down at a if and only if f prime prime a is less than 0. So either decreasing or increasing point. Finally, what about points where f prime prime a equals 0? One possibility concavity is changing at that point. The graph is concave up on one side and concave on the other. If so, the point A is called an inflection point on the curve. So we could have a graph like this, which I'll make sure to take a picture of, which would be y equals x to the third power minus 1 for negative. As we can see, it like concaves down. Like it looks like it's going up, but it's like getting like concave down. It's just getting more and more slower. And eventually it hits the inflection point, which is 0 on this graph. And then it starts increasing more. Like increasing more at a rapid rate. In the last lesson we saw these. If f has a local extreme at a, then f prime a is equal to, f prime a is equal to 0. The converse does not necessarily hold. If function prime a equals 0, f doesn't necessarily have a local extreme at a. Remember the example function of x equals x to the third power. Let's look at what the second derivative tells us in each of these situations. So f doesn't really have to, but wait, let me see. Like so like it usually is if it has a local extreme. It's f prime equals a, or f prime a equals 0, which is easier solving. But it's not always for certain graphs, so you have to be careful with that. Let's look at what the second derivative tells us in each of these situations. Suppose f has a local extreme at a, so that f prime a equals 0, and we also know that f prime prime a is more than 0. What additional conclusion can we draw? The extreme at a is the local maximum. The extreme at a is the local minimum. There is an inflection point at a. We can't conclude anything. No, there probably would be an inflection. Extreme. I thought there would be a inflection like from this graph, but it may be different. The second derivative is positive, so the graph is shaped like a smile near x equals a, so the local extreme must be a minimum. In like the graph, as we can see. It's a smile for like good increasing. Like it goes down less and less, and then it goes up a lot more. Okay, let me just see. Now let's look at converse. Suppose f has a local minimum at a. We also know that the second derivative is non-zero there. What can we clue about f prime prime a? So if it had a local minimum, I think does it technically have to be positive? Local minimum at a. We also know the second derivative is non-zero there. So it's non-zero. Well, I feel like it has to be positive, as we can see here in this example. F prime prime A is more than 0. If it's going to have a local minimum, if it has a local maximum, it's going to be the opposite. I'm going to say that. Okay, good. Since F has the local minimum at A, the graph is shaped like a smile there. The local minimum, A, FA, is at the bottom of the smile. The tangent line is horizontal there, so F prime A equals 0 as we expect. However, just to the left of the minimum, the tangent line slopes are negative. Just to the right, the tangent line slopes are positive. The tangent line slopes therefore steadily increase from negative values through 0 at the minimum to positive values as we move along the x-axis from left to right. In other words, the rate of change of f prime is positive near x equals a, that is, f prime prime a is more than 0. We can see by this. We can summarize this finding as the second derivative test. So if f prime a equals 0, then check what f prime prime is. If f prime prime a is more than 0, there's a local minimum at a. If f prime prime a is less than 0, less than 0. And then there's a local maximum at a by similar reasoning. If f prime prime a is equal to 0, we cannot conclude anything regarding a local extreme. It might be a minimum, maximum, or either. Yeah, that makes sense. Because we can also go back if f prime prime is less than 0, it's negative. F prime prime a is more than 0, then it's positive. Here are 3 graphs. They are the graphs of a function x, its first derivative and second derivative in some order. Fill in the blanks in order. So is the graph of x is the graph of f prime. What would it be? So BC. I feel like B would be consider the first. It just seems like, but A seems also like a good one too. I may think C, A. So F prime would be the exchange of it. So I bet it would be A, C, B. C, A, B. I knew B was going to be the last. I was thinking of it first, but it just seems like it would connect to another part of the graph. So we go C and then A. I guess you could see that, like how like C like is just like one little thing, and then continues to go like up and then down, and then up and then down and up. So you can see up, down, like up on C, down and then up and then up and then it'll go up, down, up, down, up, up, down, up, down. Graph C is always positive. It can't be the derivative of either of the two because those functions are not always increasing, have peaks and valleys. So the original function is C. Now it's increasing on negative x and decreasing on positive x. So its derivative must be positive on negative x. So its derivative must be positive on, and negative on positive x, which means the derivative is A. And B is the derivative of A. It is 0 where A is flat, positive when A is increasing, and negative when A is decreasing. So the answer is C, A, B. That makes sense. I guess I shouldn't be trying to go through them fast. How does the second derivative tend to come up in the real world? One way is through acceleration. Suppose we are taking a road trip, and we set the trip meter in our car as 0 as we set off. As we travel, the trip meter counts the miles we have traveled since we left. This gives a function x time that measures the miles traveled as a function of time. So zeroing out the meter sets as x0 equal to 0. Then x prime t is of the derivative given the rate of change of a function for the miles traveled ahead. This is commonly called velocity if x time is in units of meters and t is in units of seconds, and the x prime t is in units of meters per second. Say that f prime is 3,000, f prime times 3,600 seconds equals 30 translates into the statement that exactly an hour after we start our trip, the car is traveling 30 meters per second, about 67 miles per hour. But x prime t generally changes as time passes. At different times in our trip, we travel faster or slower. The rate of change of velocity x prime t is given by the second derivative of x prime prime t. It is known as acceleration of the car. For instance, if f prime 3,600 equals 30, but f prime 3,601 equals 32, then we can estimate x prime prime 3,600 equals 2 meters per second. So if it was like that, and then we can consider the increase of it. I'll take a picture. That is, our velocity has increased by 2 meters a second in 1 second. So we estimate its continuous rate of change as 2 meters a second per second, sometimes written as meters seconds to the second power. Another way the second derivative comes up in the real world is through the law of diminishing returns. This is a general phenomenon in economics that roughly says this. If the input to a production process, for example, labor in a factory, spending, and advertising, etc., is increased, each increase in the input will increase the output at a faster and faster rate until a point called the point of diminishing returns. After the point, each increase in the input will increase the output at a slower and slower rate. For example, the effects of investment in a business generally satisfy the law of diminishing returns. Each dollar invested in a company increases revenue by a larger and larger amount up until the point of diminishing returns. At this point, each dollar spent will still increase revenue, but by a smaller and smaller amount, so that relative to other investments, the company becomes less and less attractive. Let Rx be the function that represents company revenue as a function of capital invested. Based on the above discussion, what is a graph of f r prime most likely to look like? So it would be not constantly increasing. Let's see. At this point, each dollar spent I represent company revenue as a function of capital invested. What is a graph of that? I feel like it would be decreasing most likely, so it would either be 3 or 4. See if there's any hints. No. I think it would be 4. 3. The second derivative must be positive until the point of diminishing returns, and then it is negative. So the point of diminishing returns is an inflection point and is a point where the rate of change is maximized. The answer is the third graph. There's nothing to stop us from taking the derivative of f prime prime. This is called the third derivative of f, is denoted as f to the third, or f prime prime prime. There's nothing to stop us from continuing to differing. If we differentiate a function n times, we get nth derivative of f, which is denoted as fn, or it could go infinite. These higher order derivatives don't tend to correspond to real-world phenomenon directly. Although in physics, the third derivative of position, that is derivative of acceleration, is called the jerk, and does come up sometimes. Higher derivatives will be important for us when we look more carefully at Taylor series. We will use higher and higher order derivatives to get better and better approximations of the original function. Lesson complete. Okay, let's go on to real-world derivatives with real-world problems. See how derivatives are used in motion, geometry, and learning curve problems. Real-world derivatives. In this lesson, we will look at functions that model things in the real world and see what their derivatives mean. The first example should come as no surprise. If time tells us the position of a particle traveling a long number at time t, then as we've seen, f prime t tells us the velocity of that particle. A positive velocity means a particle is moving to the right. A negative velocity means it is moving to the left. We saw in the last lesson, f prime prime t is the rate of change of velocity, is called the acceleration of the particle. A positive acceleration means the velocity is increasing, and negative acceleration means it is decreasing. When you put your foot on the brake pedal in a car, your velocity is decreasing. So acceleration is negative, even though you're continuing to move to the right. F is increasing, F prime is decreasing, and F prime prime is negative. So it's kind of like a chain reaction. If F prime prime is negative, and then it pushes F prime until it hits negative. You throw a ball straight up. Its height as a function of ft is given by the graph. What statement is true? So acceleration is positive from A to C and negative from C to B. That could probably. Acceleration. I think that would be velocity is increasing from A to C and decreasing from. I feel like acceleration is negative the whole time. Acceleration is negative the whole time. I guess it probably, yeah. You could also look at the frown. I guess you could solve, and you could also see how it's going slower and slower until it reaches a point where it just drops. So I guess I'll get the explanation, but I understand it. It's really annoying when you know something and then you get it wrong and then you realize like how easy it was. That happens a lot. So explanation. Sometimes it's good to try to understand what's going on before looking at the answers, which might be confusing. The ball goes up, reaches its maximum height at point C, and comes back down. The derivatives are positive from A to C, negative from C to B. Since the derivatives represent velocity, this makes sense. The velocity is positive, the ball goes up, and negative, the ball goes down. Velocity is itself changing the whole time. It's getting smaller and smaller from a large positive value at A to 0 at C to a large negative value at B. This is similar to the question from the previous lesson, in which we saw the first derivative is going down the whole time. So the second derivative, acceleration, is negative the whole time. It turns out acceleration isn't just negative the whole time. It's a constant function with values approximately negative 9.8 meters a second which is basically the gravitational force of the Earth, the maximum. That would be the maximum, though. I don't think you're gonna throw a baseball that far or that high. I mean, you probably could, though. That reaches 9.8 meters. That usually happens a lot for, maybe, probably, I bet, skydiving and stuff. Maybe not. And definitely for, big rocks or asteroids. Suppose a particle moves along the number line, and this is the graph of its velocity as a function of time. Select all the true statements. So as we saw here, acceleration is negative. The particle is not. Particle is moving to the left. B and D. I think it would be. Particle is moving. Well, I feel like it just reaches 0. Particles at time C is where it started. Where it started at time 0. Particles not moving at C. No. Particles moving to the left. Not all the time. Particles acceleration is negative between C and E. I don't know. At least I got one. Particles not moving at C. I guess it'd be technically, since it hit 0, particles moving to the left. Let me see why that. Because, yeah, I probably would understand this one, but definitely not. But for the second one, the particles moving to the left between C and E. Let's take the statements one by one. Remember, the graph represents velocity, not position. Between A and B, the particle is moving with constant speed, so the first statement is false. I don't know, I feel a little dumb there. But at time C, the value of velocity is 0, so the second statement is true. Between C and E, the velocity is negative, so the third statement is true. Now deceleration means the whole velocity is decreasing. Clearly it's happening between B and D, but it's not happening between C and E. As for the last statement, the velocity velocity was positive the whole time from 0 point to point C, so at C we are not where we stay. So at C we are not where we start. That would make sense. Whenever we have a function, when we input variable represents the time, the derivative is interpreted as the continuous rate of change with respect to time. For example, suppose a certain species of insects is introduced on an island, and then P time give the population of the species at time T. Suppose that the population always increases, but after a while it starts to approach a finite value. Consider these three statements. P prime is positive, P prime prime is positive, and P prime prime is negative. When it starts its approach in terms of derivatives, what is happening? So when it starts its approach in terms of derivatives, so I would say 1 and 2. 1 and 3. We're told that the population is increasing, so statement 1 is certainly true. But what does leveling off mean in terms of the second derivative? Consider this graph. Yeah, I guess it's technically decreasing. You could see it as a frown too, as the population gets bigger and bigger, it slows down and down. Leveling off implies that while the graph is still increasing, it's increasing by less and less. In other words, its rate of change is going down, so the second derivative is negative. This is corroborated by the fact that the graph here is concave down, which from the last lesson corresponds to a negative second derivative. So I can understand this. So the first derivative would still technically be positive because it's up below any negative levels and is not going down. But derivative prime is how much it's accelerating. Like, you could see, like, as it slows down, it's technically negative. But, like, but prime is still positive. Because it's above, not going down. In learning theory, one talks about how much information is learned as a function of time spent learning. These are called learning curves. Suppose we have two school subjects, and L1T represents the information learned as a function of time for the first subject, and L2T for the second subject. Perhaps these functions were determined by analyzing student performances. In the first subject, if the first subject is more difficult, which do we expect to be larger? F'1 or F'2? So, student determined by student performances. So, what F'(T) is it? 2 is if it's positive or negative. If the first subject, we should expect to be larger. Would it just be F'(2) if, like, people expect to be larger? So wouldn't it technically be larger? The prime would be, or the derivative, as it goes up. It'd probably be positive. I was worried they get it wrong. Like, there may be at one school where everyone likes the hard classes. You never know. The derivative represents the rate of information gain. That is how fast you're learning the subject. If L1 is hard, we expect the rate to be smaller, at least at the beginning of class. A commonly heard phrase is that a subject has a steep learning curve. This is usually taken to mean that the subject requires great effort to learn at the outset, corresponding to a small derivative in the learning curve. Remember, if a subject is difficult to acquire initially, the rate at which new information is gained is small, corresponding to a small derivative. Hopefully that's not me with calculus. This is definitely hard. I know. Here are learning graphs for two classes. Both measure information gained as a function of time spent. Which graph corresponds to the class with a steeper learning curve at the beginning? It would be B, because B is less knowledge learned. Of the first two options, A has a smaller derivative initially and therefore corresponds to the subject's steeper learning curve. There's a fair paradox in this phrase, steeper learning curve. That's worth thinking about. The colloquial use of the phrase refers to the difficulty of learning a new subject. The learning curve, however, measures the acquisition of new knowledge about the subject as a function of time. If the learning curve's rate of change is small, it takes a significant amount of time to gain If the learning curve's rate of change is small, it takes a significant amount of time to take a appreciable amount of new information. This indicates a higher level of difficulty. In short, a small rate of change in the learning curve measures a high degree of difficulty in learning the subject and corresponds to what is commonly meant by a steep learning curve. On the other hand, looking at a graph from a purely geometric viewpoint, we would claim that it, or part of it, is steep if the rate of change is large, corresponding to a large derivative. It's important to be consistent in use of terms in mathematics, otherwise confusion is unavoidable. I guess it does start steeper, you can see. Yeah, you can definitely tell it's steeper. In our real world examples so far, the input variables has been time. It's common to look at derivatives when the input variable represents space too. For example, we might have a function Tx that tells us the temperature x units along a metal rod. Then T prime tells us when we move a little to the right by the factor of the move that the temperature changes. Suppose we have a rod of length L, and this is the graph of y equals T prime x. So this is the whole rod and its temperature. What is the coldest point on the rod? Would it be the lowest point? That tells us the temperature x units along a metal rod. And then you write the factor to move the temperature changes. So it starts. So I feel like it would be T. Oh, 0. Here, let me just go back. Think of a bug traveling across the bar from left to right. From points A to E, temperature is decreasing because T prime is negative. After E, the temperature starts increasing again. So the lowest temperature must occur at point E. So that means it's basically saying that would be. So, There are also interesting examples to consider when the input value. So D would be the coldest. Warmest. I guess it shows how it's decreasing or increasing. E has the most rapid change. Think of a bug. Points A to E, the temperature is decreasing because T prime is negative. After E, the temperature starts increasing again. So I guess it's so it is basically negative the whole time except past E. So it'd be considered the coldest, since that's the only point where it increases. Or after it increases. There are also interesting examples to consider where the input variable is neither time nor space. Suppose we're filling a tub with water, and left Ft tells us the volume of the water in the tub at time t. This is similar to other examples we've seen. If f prime a is more than f prime b, that means the rate of water entering the tub at time a is greater than the rate entering the tub at time b. But now let's GV be the time at which the amount of water in the tub is V. So if G equals 100, so G 100 equals 10, that means it takes 100 seconds. It takes 10 seconds for 100 units of water to enter the tub. Okay. Suppose that G prime U is more than G prime V. What can we conduct about the rate of water entering the tub when the volume is U versus when the volume is V? I feel like it would be A. And like if it's greater, it probably would be. It must have been with the primes. We'll use the input nudging view of derivatives. Imagine we are at U, so the volume of water in the tub is U. We increase U a tiny bit, say, to U plus E. The derivative G prime U times the nudge tells us how much the output changes. In other words, it tells us how long we have to wait for the water volume to rise by E. Similarly, if we start at V and nudge it by the same amount, the derivative G prime V times the nudge tells us how long we have to wait, starting at volume V, for the volume to rise by E. Now, so it is like change. Now, if GU is more than G prime V, then we have to wait longer for the water to go up at U than at V, which means water is entering the tub more. So F and G are inverse functions. We'll see later that basically derivatives of inverse functions are multiplical repersals of each other. This accounts for the perhaps surprising answer to this question. To finish this lesson, let's look at derivatives in a completely different context, area from geometry. So hopefully I'll be able to do this. Let AR give the area of the circle of radius R. Of course, we know the formula for AR, but that doesn't matter for this question. Let's interpret A prime R using the input nudging view of derivatives. We imagine increasing the input R by a little bit, say rate of change R. So that's how much R would increase. How much does the area of the circle change approximately? R times the radius. I would say circumference, believe. Yeah, because it surrounds a whole circle. Don't worry, I still know my geometry, and I'm learning it from someone right now. First, here's a rough visual approach. The additional areas caused by the outer ring in the picture. The area is approximately equal to width, rate of change R, times its length, the circumference of the circle. This approximation gets closer to the true values as the rate of change of R gets small. That means that area prime of R is just the circumference of the circle. A more careful approach here is algebraic. The area formula is pi times the radius squared. The area of the original circle is therefore pi radius squared, while the area of the larger circle is pi r plus rate of change r to the second. Taking the difference between the two areas gives us, we can see that this pi 2r rate of change r plus rate of change r to the second. We expand the square r plus change rate of change r to the second above and cancel the 2r to the second terms. Now, rate of change r is supposed to be a very small number, so rate of change r to the second is a very small number. So in fact, so small in fact that we can ignore find the approximate difference between the two circles to be 2 pi r rate of change r. We recognize that 2 pi r is the circumference of the original circle. So we can see here. It also can be pretty easy. You could also just do the circumference and increase at the change. It's just like making the circle bigger. But it would be considered acceleration as you increase it at the same rate, but it gets bigger and bigger. It maybe would be considered deceleration at a point, or like almost like the frown. Because if it gets too big, then the rate of change r is nothing, or will be nothing. Or I guess it's never really, because it always is increasing. So it probably would be. Probably wouldn't be none of those graphs, actually. Because it still is technically increasing, just increasing at a slower and slower rate. So I guess it would be deceleration still. Well, not velocity, right? Wise. Or like a upside or a downside. From the last problem, the derivative of the area of a circle is its circumference. That's a nice intuitive exambulation of what derivative means. The rate of change of area is the boundary to the area of the circumference. We'll see later how to differentiate formulas, but you already know you can check that if r equals pi r to the second, then a prime r equals 2r, 2 pi radius. I'll take a picture of that. Let's try the same thing for a square. Let AS give the area of the square and side length S. When S is increased to S plus the rate of change of S, approximate by how much of the area does the square increase. Let me just read this. Times half of the perimeter. In the picture below, we see that we add a horizontal and a vertical bar dimensions roughly as S times rate of change S. So the total area added is 2S rate of change S, or rate of change S times half of the perimeter. That would make sense. So the derivative of the area of the square is half the perimeter of the square. And we can finish this. I guess you could use a line geometry, which is interesting. That could also used for increasing and decreasing sizes. I mean, I'm definitely going to use that. Now I know what class. And now let's finish our last lesson of derivative, main derivative area, the average versus continuous. Average versus continuous. Here's a simple example to get us started. Suppose function t is the different distance traveled in miles on a car trip. Say t is in hours. Suppose that f1 equals 50 and f3 equals 190. Then the car traveled 140 miles in 2 hours between t equals 1 and t equals 3. And we will say that its average velocity over that 2 hour stretch is 140 divided by 2, or just 70 miles per hour. More generally, the average rate of change of a function f between x equals a and x equals b is the total change f in f divided by the change in x. And that is the average rate of change of f is fb minus fa divided by b minus a. Doesn't this look familiar? We've defined the derivatives as f prime a equals the limit of x equals a, which is f function a minus function function x minus function a divided by x minus a. Yeah, I remember that, definitely, from another video I had before. I think I uploaded it. Yeah, I think I uploaded all my lessons. In other words, the continuous rate of change, that is the derivative, is the limit and average rate of change over smaller and smaller intervals. Visually, the average rate of change of f between a and b is the slope of the segment line connecting a at function a and b function b. We see once again that the slope of the tangent line, that is the derivative, is the limit of the slope of the segment lines. So look in this equation. So b minus a, and it could also look like a triangle. Well, that's kind of what they're trying to show. That's b function b. It's function a minus b, function b minus function a, and then b minus a. Now let's go back to the car trip example from the previous problem where the car traveled 140 miles in 2 hours. Consider these three scenarios. Scenario. Yeah, I feel bad for second graders and younger people. They usually start with just average 70 miles per hour or something, and just continuing. I mean, not all of them, but a lot of them. Most of them that are taught like that. And then maybe when they get into high school, they have to learn that that's not always going to be like it. In real life examples, no one's going to be driving at 50 miles per hour for their whole ride. Unless you're like really good at keeping their driving speed. Okay. Now let's go back to the car trip example from the previous problem where the car traveled 140 miles in 2 hours. And to consider these three scenarios. A, we start out going 50 miles per hour for a while, but then decide to speed up and keep going at 650 for the rest of the trip. We set the cruise to control 75 miles per hour for a while, then slowed down and stopped for gas for a bit, and then accelerated back up to 75 miles once we got back on the road. We drove at a constant speed of 75 miles for the entire 2-hour period. Possible description of a 2-hour period. I feel like constant speed is definitely out of the question. So we go at 50 for a while, but then decide to speed it up and keep that. I feel like it would be B. Yeah, because I feel like if we were 50 miles per hour for quite some time, let's just say like an hour, like we might not even have enough time. And it says for a while, it definitely states that, so it's definitely meaning that we did 50 miles longer than 65. That wouldn't add up to 140. The first scenario is impossible. There's no way to average 70 miles. We never went faster than 65. Similarly, the third scenario is impossible since there's no way to average 750 miles if we never went slower than 75. The second scenario is reasonable. At times we traveled faster than 70, and at times we traveled slower. So it's only possible description of the trip. Intuition from the previous problem is that it's impossible to average a certain speed if our continuous speed is always either less than or greater than that speed. That is, if we average 70 miles per hour for the 2-hour trip, our speed mirror must have read 70 miles per hour at least once during the time span. Let's put it another way. If the average rate of change function of x between x equals a and x equals b is s, then there must be at least one point c between a and b where f prime c equals s. So s has to be between a and b, basically. This statement is called the mean value theorem. Mean is just another word for average, or MVT for short. Though it sounds a little abstract, it has real-world applications. For instance, if we're on a toll road with a speed limit of 55 and the toll cameras show us passing through checkpoints, 140 miles apart in a 2-hour period. The NVT says that we must have been going exactly 70 miles per hour at some point, even though there is no way to tell exactly then. Since if we went below it, like the whole time, that wouldn't be possible. So we might get a speeding ticket without actually getting caught in the act of speeding. Visually, this says there must be at point C where the tangent line is parallel to the green segment line below, but since the segment line slope is FB minus FA over B minus A. So there has to be a point where they meet, because it wouldn't be possible. We can see by the graph how, like, if even like we're lower, we're gonna have to meet that point at least once in the trip. Might not even been that for long, but we had to do it at least once. We can see how the graph meets it once. Right here. Up here on the top. By the way, the theorem says at least one x value. There may be more than one. If function of x is linear, then function prime x is a constant equal to the average value. This corresponds in the car example to keeping the speedometer pegged to a constant 70 miles, so every x value would satisfy function of x prime equals s. So there may be some constant. Here's a simple example. A function of x equals x to the second power a equals 1b or equals 2. The NVT says that there is at least one point C between a and b where the derivative f prime c equals the average rate of change of fx over the interval ab. It turns out that this particular f that there is exists. It turns out from this particular f that there is exactly one such c. What is c? So it would have to be a point between these. Would it be c equals 3 over 2? That'd be considered like about like 1.5. Prime 2 would probably I don't think 1.0 FC equals the average rate of change fx over the interval. So it has to equal it. So it has to equal at least 2, which I believe none of these do. The average rate of change of f over the interval is f2 minus f1 over 2 minus 1, or equals to 2 to the second power minus 1 to the second power over 2 minus 1, which would equal 3. The derivative of the point C is f prime C equals C 2C. So the value of C guaranteed by the NVT is a place where 2C equals 3, or C equals 3 over 2. Note that this is where the slope of the tangent line to the curve y equals x to the second is parallel to the slope of the second line x equals a and x equals b. This is where the NVT guarantees that those will at least happen once between a and b. So it has to be exactly at the point. We can see how it meets exactly. How the average graph, it meets at least once. And you go up here, C. You can see a meet at C. It has to be parallel to the green. Let's continue. There is one assumption of the mean value theorem we left out. Now let function prime equals the absolute value of xa, or equals -1, b equals 2. What can we say about the mean value theorem for f between xa equals xb? Between x equals a and x equals b doesn't hold because, well, I believe f equals absolute value. Would that be corners or steepness? Here, give me 1 second. Hopefully this isn't considered cheating. So it would be considered a corner. So it doesn't hold anywhere. Yeah, it doesn't have a derivative because of the corner-like graph. The average value of function of x is 2 minus 1 over 2 minus 1 parentheses -1 equals 1 over 3. But the derivative is never 1 over 3 in the interval. The slope of the tangent line to the graph is neither -1 or 1, and there is no well-defined tangent line at the point x equals 0. So it appears f needs to have a derivative everywhere in the interval for the NVT to work. Note that function of x equals the absolute value of x is continuous, but it's not differentiable because the curve is not smooth at x equals 0. Or it could be considered corners, as we can see here. Suppose f is differentiable everywhere and fa equals fb. Then the NVT says that there is a point C between A and B such as we can see example, which equals 0. That is, there is at least one point where the tangent line is horizontal. So if they do equal, there has to be horizontal. If it's not, they have to meet somewhere. Or it has to be C. This special case of the NVT has its own name. It's called Rowley's theorem, and it's not too hard to see why it's true. First, if the graph of the function is just a horizontal line, then the derivative is 0 everywhere. So that's an easy case. If it's not a horizontal line, then let's just say the function takes values above function A. Then by the extreme value theorem, or EVT, there's some point C between A and B where the function has a maximum. Since this isn't one of the endpoints, it's not only a maximum but a local maxima. That is the top of a hill. We know that therefore f prime c equals 0, and that proves Rowley's theorem. We can prove that NVT starting with Rowley's theorem. Let function of x be a function defined in the interval a, b, which has a derivative everywhere in the interval a, b. Additionally, let s equal fb minus fa over fb minus a. We need to construct a function gx satisfying these criteria, which would be ga equals gb, which equals 0, so they have to be equal, and gx equals function of x, and it has to minus s. If we can find such a gx, then the proof of the NVT goes as follows. Since GA equals GB equals 0, Rowley's theorem guarantees that there is at least a point C between A and B such that G prime C equals 0, but G prime X equals function of X minus S. So 0 equals function prime C minus X, and function prime C equals S. So it basically would be the same with 0. So these would be the same equations. Gx equals 0 and Ga equals Gb equals 0. Which one represents Gx? Maybe this A. Oh, let me see. Y. The function gx equals fx minus fa minus x times x minus a satisfies both ga equals 0 and gb equals fb minus fa minus s times ba, which will equal fb minus fa minus fb minus fa over b minus a, b minus a. Also, gx equals function x plus a linear equation, negative function of a minus s times x minus a. Remember that function of a, s, and a are constants, so the derivative g prime x is equal to f prime x plus the derivative of a linear function, which is just the slope of the line. The slope is negative s, so gx equals function of x minus x. These are two facts about the gx which are needed to make the proof work. We can see in this picture. The NVT allows us to prove that some of our natural ideas about the derivative are in fact correct. For instance, suppose that f prime x is more than 0 everywhere in some interval. Then we expect that f is increasing in the interval. Now here's formal proof. Take any two real numbers a and b in the interval with a is less than b. Then the NVT says that there is some c between a and b, such as function of prime c equals function of b minus function of a, or b minus a. Since function prime c is positive and b minus a is positive, function of b minus function of a is positive too. So function of a is less than function of b. This shows that f is increasing. Similarly, we can prove that if function prime x is less than 0 on the interval, then f is decreasing. And if f prime x is equal to 0 for the interval, then f is constant. Suppose function of x is a function whose derivative exists everywhere. Suppose the equation f prime x equals 0 has exactly one solution. Which of these statements cannot be true? So has no solutions. So this one, 3. We want to show if f prime x equals 0 has exactly one solution. Then it is impossible to have function of x equals 0 at exactly 3 different points. To prove this, we'll use the method of conjunction. We'll assume that function of x equals 0 does not exactly 3 distant solutions and demonstrate that this leads to an impossible reluctant conclusion. Rolle's theorem says that function of a equals function of b equals 0, that there is a point between a and b where the derivative vanishes. So that if there are 3 places where f vanishes, say a1, a2, and a3 is increasing order, and there has to be at least 2 places where f prime vanishes, one between a1 and one between a2, and another between a2 and a3. This is impossible, so the equation function of x equals 0 now have 3 solutions. That would make sense in the smile and frown problem with increasing and the acceleration until with the frown how it increases slower and slower and then decreases faster and faster and the opposite way around. You can't have 3. You can do a big thing like that. So I don't know if someone's going to be making that face. To show that the other statements can be true, we'll look at a few examples. First, consider function of x equals 1 over 1 plus x2. Since the output is always positive, f can never be 0. On the other hand, f prime x equals negative 2x over 1 plus x to the second, parentheses second, which 0 once and only once, namely at the origin. Now consider a function of x equals x to the second. The equation f prime x equals 2x equals 0 has a singular solution at the origin, as does f function of x equals 0. We can use the quadratic function to show that f prime x equals 0 having a single solution to compatible with function of x equals 0 having exactly 2. Take f function of x equals x2 minus 1. The equation function of x equals 0 has exactly 2 solutions, plus or negative 1, while function of x equals 2x equals 0 only at the origin. And that's that. That's quite confusing, I have to say. And that's it. That's the 3 lessons I'm doing today. I really liked it. Sorry that I rushed at the end, but probably shouldn't have read as fast. But I appreciate you for watching. I know no one really watches here, but if you do watch or skip to here, I just want to say thank you for watching and even trying to watch for a little bit. I appreciate it very much. Not much people watch my videos, so any views or any comments I really appreciate. I'll make sure to respond to any comments if you have any questions, and thank you so much for watching. Goodbye.